Welcome to Open Source Spotlight. We invite open source authors and ask them to show the tools they're working on. Today we have Philippe. Hi, Philippe. Tell us a few words about yourself and about the tool you want to show us.
Sure. Hi, thanks for having me. My name is Philip. I am working on a company called ParadeDB. We do search and analytics in Postgres. We're essentially a competitor to a tool called Elasticsearch for companies that want, or companies, hobbyists, whatever, that want to build projects. We do user-facing search, user-facing dashboards or analytics. We enable people to do that through Postgres without needing to start to denormalize their data or operate two different data stores and do data movement between the two of them, so on and so forth. So we're built as Postgres extensions. You can install it in your primary Postgres, or you can connect it as a read replica on your hosted Postgres. And yeah, that's what we do in a nutshell.
I would be interested to see this in action.
Sure, let's do it. Okay, so ParadeDB is an Elasticsearch alternative. We're deployed in two main ways, one via Kubernetes and via Docker. For today's demonstration, we'll focus on Docker. If you go to our GitHub repository, github.com/paradedb/paradedb, you can see instructions to pull our Docker image. So on a brand new environment, you can go ahead and do that right up. It's going to go and spin it up. Afterwards, you can connect to our Docker image. It's a standard Postgres with a few of our extensions installed via a standard psql command. We're going to keep this running in the background and then run a new terminal. And here we go. So we're in. This is standard Postgres. ParadeDB has two main benefits for users. One, we enable customers to avoid needing to go and learn about Elastic, denormalize their data from Postgres, so on and so forth. All of that is handled by our API to do full text search and analytics in Postgres. The second benefit that we offer is the ability to remove the need for complex ETL and data movement between your primary Postgres and your Elastic, and we do that via our ingest API. Our ingest API is built by integrating DuckDB inside Postgres. For those that are not familiar with DuckDB, it's an in-process analytical database which can fetch data from wherever it may be. So if you have data in various file formats in addition to your primary Postgres, or if you have data in cloud object storage like S3 buckets, or even in big data table formats like Apache Iceberg or Databricks Delta Lake, you can fetch that directly with ParadeDB. Of course, if your data is already in Postgres, you don't need to do any of this, but we'll cover that in a second. The way we do this is by creating a foreign data wrapper which integrates our DuckDB extension. Here, we'll show you how to do that. So first, you can specify a foreign data wrapper. In this part of the demonstration, we'll show you how to query data stored in Parquet files on AWS S3. So first, we can create a foreign data wrapper, specify its name, and then finally, you simply need to create the Postgres table name that you'll have and then specify the file location. If you have specific credentials, if it's a private bucket, all of that is covered in our documentation. But for all intents and purposes, we're going to skip that for today's demo. So now I've created a foreign table. It's possible for you from ParadeDB to start querying that Parquet data as if it was a Postgres table. So let's query for the vendor ID, passenger count, and trip distance, and let's just return the first row to see what it looks like. So in this case, the data set is taxi trips taken in New York City. You can see who the vendor ID is, how many passengers were at that trip, and the distance in miles, I believe. You can also do fast analytics over that data thanks to DuckDB. So if you go and we run a select count star, in this case, you'll see we actually aggregated and counted over nearly 3 million rows, quite fast, significantly faster than you would do normally in Postgres. And then lastly, you can create a regular Postgres table to do this. This is what enables you to create full text search indices and have Elastic-like workloads done directly in ParadeDB. So let's create a copy of this table that natively stays in Postgres so it can have indexes created on top of. In this case, we'll only fetch, say, 100 rows. And then we can go and select everything from this trips copy table in this case. So we could say select count star from trips copy, and then you'll see we have 100 rows, and we create a search index on this. This is possible to do in ParadeDB via any of our supported file format extensions and so on. This is the easiest way to get data in without needing to manage data pipelines. Now, once you've completed this, or if you already have data in Postgres, you can turn to our API. The primary value prop that we give customers is the ability to do full text search in Postgres. The more Postgres savvy of you will know that Postgres itself already has full text search capabilities, which is true, and it's quite good, but there's a few limitations that ParadeDB adds on top of it. First of all, the ParadeDB search indices are ranking based on an algorithm called BM25, which is the state-of-the-art relevance ranking algorithm in search engines today, like Elastic and all the other popular ones. This is why you'll see some functions name in ParadeDB called score BM25 or create BM25, like you can see here. This will allow you to have better search relevance ranking than if you're using native full text search in Postgres. Second, we also give customers the ability to do tokenizations in more languages than the native Postgres full text search, and we'll cover this in a second. Let's see an example of a search query we run in Postgres. First, we can create a mock table that we ship to show what it's like, and later we can also revert to create a search index directly on our trips table if we wanted. If we look at it, every ParadeDB Postgres installation will ship with this mock data. There's about 40, 50 rows in it just to get people poking around. This is what the schema looks like. You have a description, a rating, and then a category of the good. When you want to go and create a search index in Postgres, in ParadeDB Postgres, excuse me, we use the create BM25 API, which will create a BM25 search index to give you that accelerated performance. When you do, you create the name, you specify the schema, you specify which table you want to create on top of. In this case, it's our mock item, but if we wanted to do it on our trip table, for example, that we were looking at here, we could do that as well. And then you specify which fields you want to tokenize and how you want to tokenize them. So in this example, we're tokenizing the description field, which is here. We want to tokenize it in English because it's written in English. And we also want to tokenize the category field, which also has text. And finally, we have a numeric field that's tokenizing the rating. So let's go ahead and create our first BM25 index. That's completed. As soon as that's completed, you can start running search queries. So for example, here, we can select, we do a search where the description is keyboard or the category is electronics and the search rating is above 2. This is a relatively simple search query. You could also do it in Postgres full text search. As I run this, you can see here, let me make this a little bit easier to see. Here we go. You can see all the items that we're returning that matched the electronics category, for example, and have a rating above 2. We can do more complex searches, of course. So let's search for Bluetooth speaker, but let's say we also want to surface results where there might be a word between Bluetooth and speakers. So ParadeDB supports the slop operator and all the standard operators that you might see in Elastic, like regexes, whatever it may be. We can see them all the way here, and we'll cover that in a second for the advanced search query. Highlighting, snippets, regexes, edit distance, so on and so forth. So let's look for that in our trip here. Anyways, so as I was saying, we can go and look for a Bluetooth speaker where there's an edit distance of 1 word between the word Bluetooth and speaker. That can allow you to build more complex search experiences than you would be able to do otherwise. So if we keep with our original example, you can see here we have Bluetooth enabled speaker in our description. And by creating a search query like this one, we can go and surface it and then be surfaced to your customers or to your users. Lastly, we can tokenize in a variety of ways. Here we only have a data set in English, but it's possible to tokenize in Chinese, Japanese, Korean, Arabic, Czech, French, English, Spanish. All major languages in the world are supported. And we can also do tokenization like source code. For example, if you're building a developer tool or lowercase, whatever type of transformation you might want to do on your textual data. In this example here, we'll keep the same mock item table that I was demoing previously. We can inspect the schema once again. Here we go. And we can go and tokenize it based on the n-gram tokenizer. What the n-gram tokenizer does is it simply splits the word in chunks of size n, whatever size you might want it to be. For a lot of use cases in Postgres, there are extensions that exist to C called pg3gram, which you may need to go and install directly, but it's bundled into ParadeDB. So let's create a separate index. you can go and create multiple indices on the same tables or on the same subset of tables to facilitate indexing or offer different experiences to different users. That's complete. Then we can go and start looking for the description blue. Here we go. So even though we only search for the word blue, thanks to our n-gram tokenizer, we were able to, here, let me show you. Thanks to the n-gram tokenizer, we search for keywords of 4 characters, minimum 4, maximum 4. And you could see we have the word blue, which fits within this long keyword and was able to be found thanks to this tokenizer. Lastly, let's show you how you can retrieve those BM25 score and do some relevance ranking that you wouldn't be able to do in Postgres normally. So we have a snippet function that allows you to examine this BM25 score and highlight specific snippets of your results. Again, from the same search index we created, we can go and run another query for description blue, and we want to highlight the field description. As you can see here in the search response, we have highlighted blue out of the entire text that we were searching for, and we've displayed the BM25 score. The higher the score, the higher the relevance. And so if we're searching a data sets that may have 10, 20 millions, let's say, results, you'll see them all rank from top to bottom based on the limit that you're exposing. In the demo today, we're using a pretty small data set, but in reality, ParadeDB is deployed on up to 10 terabytes clusters in the wild today with some of the large organizations around the world. Lastly, we can go and show you as well combining the results to see that next to the data. So it's possible to see the snippet and see the score BM25 next to the original data to build that experience that I was just describing, where you might want that to be user-facing. So following the query here, you can see, here we go. You can see the description. This is cutting a bit through the terminal, I apologize, but you can see the Bluetooth speaker is the description, the snippet is here, and then the score is being cut off here. That shows you what the original search keyword was being returned from this query. Okay. Lastly, we can do a demo of a search product nowadays without talking about AI and vector search. So that will be the final segment for us. But for anyone that's interested in going into the depth of full text search, we have an advanced search query section of our documentation, which I'll skip for today, and is where most of our power users spend their time. ParadeDB is built with Postgres. We support PG Vector, the standard vector and Postgres extension. I'll go a little quickly over this because PG Vector is a pretty known tool nowadays, and we don't make any key modifications to it. But ParadeDB does integrate with it to give you the ability to do hybrid search, which is the state-of-the-art search experiences today here. So just like you would with normal PG Vector, you can go and create PG Vector search indices like you see here. And ParadeDB has the ability to build on top of this to allow you to do hybrid search. So let's look at it here. I'm going to skip the vector search function and focus specifically on hybrid search. What our hybrid search function does is it combines the BM25 indexes that we created above with the HNSW vector index that we just created and allows you to rank the query based on relative weight between the two. This is what every major service that does search today does to combine both semantic meaning and keyword-based meaning to return results. It's very common in e-commerce, very common in financial technologies, so on and so forth. So in this example here, we have our search index. We want to score for the description, keyword, or category electronic. We want to do an embedding similarity of the query, and we want to give 90% of the weight to the keyword and 10% of the weight to the similarity. So we can go and run this query here, and you'll see the result. Our score hybrid or return, you can see which of the tools have been, which of the rows, have been returned in which order based on their relative hybrid score ranking. And just like we did before, we can conclude with this. Let me expand the terminal here. You can display the results next to the score, as you can see here. So it's always possible to combine them with the regular data through a join typically. And so the description of the items, which category they are, what their vector embedding is like, and finally the score hybrid that combines both the keyword-based ranking and the HNSW ranking. And that's it for high level of ParadeDB. Of course, there's a lot more that meets the eye. You can go and look through the documentation to see all that's possible to do. Something we haven't covered is our analytics and faceted search. If you want to bucket your search results, display them to users, that's a very, very common feature. And there's a lot that can be done to do search over join tables, which is another very common feature as well to avoid denormalizing. That's it.
Yeah, that's pretty cool. So I'm wondering how much of Lucene and Elasticsearch functionality did you have to re-implement, or you somehow could use this inverted index and stuff like that from Lucene?
Great question. So the answer is a lot needed to be re-implemented, but not by us. We are built on top of a Lucene-inspired library called Tentivy. It's a Rust re-implementation of Lucene. It's an open source package. It's quite popular now. It's backed by many, many companies. Every Rust-based database that claims to have full text search has it by integrating Tentivy in it nowadays. And so we've made modifications to it, but we were fortunate to inherit a lot of it.
So like all this inverted index and like all this implementation come from there, right?
The core inverted index, yes. And then we make a lot of optimizations to make it compatible with Postgres storage, for example, avoid random lookups and things like that to optimize performance and sort of glue it with the Postgres syntax.
Yeah, interesting. Then I'm just curious, like how much is it different? What's the difference between using Lucene as backend and Postgres in this database as backend? Like in terms of, do you see the main difference in performance, in usability, in something else, or all of the above?
Good questions. I would say it's mostly in usability, both from the operation standpoint and from the search API standpoint. So ParadeDB's performance on single node is faster than Elastic, but no one complains about Elastic's performance. There's two main things that brings users to us. One is you don't need to denormalize their data. So that's a big
And by
value
that, you
prop.
mean, like you mentioned it multiple times. So by denormalizing, you mean when we insert something in Elasticsearch index, we have to do like select, join table A with table B, and basically it has to be one row before we insert to
Um,
Elastic index, right? And only then we can search.
Yeah, what I mean is Elastic stores data in document model, right, in JSONs. And so you'll need to break the table format of structuring your data in a relational table to put it into Elastic. For many use cases, it's not possible to do this in a very convenient way because Elastic's concept of join searches, where you want to combine data from two Postgres tables or two search indices in the case of Elastic, is
Even it's,
quite poor performance.
is it even possible to do that in Elastic?
So
Like to do join?
I've never run the API myself. It is
Like,
possible. I
why
don't.
would somebody do that? Okay, like this
Um,
is like maybe for a separate discussion, but I see the I see the benefit of ParadeDB. Like for example, if I already have, like I don't know, let's say I have a marketplace and then I have different items, and these items already have description, title, and so on. Like instead of just putting this data to Elastic and have like a special process, I can just have a replica with ParadeDB and then have the text search out of the box without doing anything, right?
correct, exactly. That's the second value prop. Customers don't need to operate these two data stores. It's very common for people to have issues where they send data to Elastic, but then maybe the insertion fails. So now you have two different states between your search engine and your relational database. It's very difficult to reconcile that. You need to rebuild indexes because Elastic's indexes are immutable. It's not quite real time. Usually people will batch their ingestions from Elastic. ParadeDB is real time. So for all these reasons, especially e-commerce is a good use case, like where the inventory might change quickly, for example, right? Promotions, whatever it may be that wants to be applied to products. It's a lot simpler to keep everything in Postgres through ParadeDB.
Yeah, and I'm just curious, how many people are working on ParadeDB?
We're 4 people.
Or people full time, but I guess there are also external contributors, right?
we've been fortunate to have a few external contributors. We welcome external contributions, but the vast majority of it has been written by the core 4 people.
And if somebody wants to become an external contributor, what should they do?
They can go to github.com/ParadeDB. You can see all of our repositories. We mostly work out of a main repository called ParadeDB, and we have contribution guidelines. We also have a Slack community, which is linked in the README, where people can join and talk about the contributions they might want to make or ask for help making issues. And then we work off of GitHub.
It's implemented in Rust, right? I think you mentioned that.
Correct. It's
Yeah.
implemented in Rust as Postgres extensions via a framework called PGRX.
Okay. I have not heard about this thing before, but now I know.
Yeah, unless you want to build Postgres extensions, you
Yeah.
probably won't hear about it, but it's quite
Mhm.
popular. And every major new Postgres product nowadays, almost all of them make use of this framework.
Yeah. What are your plans for like short-term plans or middle-term plans?
Feature-wise, you mean?
Feature-wise, like what do you want to work on in the next quarter?
Yeah, good question. We will be changing a few things about our API. We're planning to implement this thing called a custom scan, which will allow us to be even more Postgres idiomatic in the user-facing API. That will remove some of the sore points that can trip users sometimes when it comes to doing to implementing search queries. That's going to be a big one. We're also working on optimizations to those join indexes that I was mentioning. So create an index over a subset of columns from 2 different tables to avoid needing to do these complex joins that can be very low performance. That's another big one. And then on top of this, we have some other analytics capabilities to speed up count star, not just on remote data, but on local data. Integrate that with our faceted search, for instance. So we're also working on that.
Okay, awesome. Do you have any advice for anyone who's watching this?
About what?
Life, Postgres, career?
Just use Postgres. Just use Postgres.
Okay.
I think what I've learned is the the smaller organizations and smaller projects always think that often think that their needs are very complex and they need very complex tools. And the really big organizations, they have very, very complex needs, yet they define them in very simple ways, and they just use Postgres. And it makes their lives a lot easier.
Yeah, actually, I second that because, like, I see now the tendency of like with vector search, there are so many vector databases, but people already have Postgres. Like, why not starting with evaluating Postgres and then seeing if using an external one adds anything on top of what you already have, right? So start with
Yeah.
what you already have.
Exactly, exactly. Usually, when people come to us, they say like, "Hey, using full text search and vector search in Postgres sounds really easy, but is it going to scale to X amount of data that I don't have today?" Right? And what I always say is, well, one, the answer is yes, but two, you don't really have that data today. So start with what is the simplest way to do it today. But ParadeDB today, our biggest cluster is 12 terabytes, and so we haven't reached the petabyte scale, but it's reached a point where Postgres can actually carry go a very long way for most
Mhm.
people, even quite mature organizations.
But I guess if you have a petabyte of data, maybe Postgres is not always the right tool.
Yeah, look, at that point, we haven't done testing on a petabyte yet. One day we will, but not yet. And so I wouldn't go as far as to say you should do that in this case. Yeah.
Okay. Okay. Thanks, Philippe. That was awesome talking with you. And thanks for doing this in open source. And please, everyone, do not forget to give them a star.
Good. I appreciate it.
Okay. See you around. Bye.
Thank you so much. Ciao.